Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe, like, and share my videos, which are intended for the civil engineering community. I hope that my videos will help you in your studies, and I hope that you can follow the discussion, the explanations that I give in these lecture videos. And I hope that you will enjoy watching. So in this video, I'll discuss Pascal's laws and intensity of pressure, variation of pressure with depth. So let's have uh, Pascal's laws, and I attempt to explain it well so that you can follow the principle and hopefully use them in the analysis by solving associated problems with this topic. So the intensity of pressure is normal to the plane of contact when the fluid is at rest. So to help explain why should the pressure be perpendicular to the plane of contact or to the surface of contact, so let's have here a picture of, let us say, a body of liquid. In this case, let's have a body of water. So let's assume first that it is possible that for this body of water to look like this when it is at rest. So let's consider this section, plane section, and let's consider the free body diagram above that section, plane section. So it consists of the weight. Then let's draw the axis perpendicular to the plane, which this plane makes an angle of theta with the horizontal. So the angle between the weight, the vertical, and the normal or perpendicular to the plane is also theta. Now, of course, the weight has component parallel to this plane section, and that's it. It is W times sine of theta. Then for this plane, this surface of contact, we have supposedly friction, and which is zero, and the normal force. Now the reason why friction is zero, because we can never see a liquid that is uh, at rest when the plane is inclined like that. So it means that this will slide until such time that the surface should be horizontal or flat. So that proves that friction cannot develop when the liquid is at rest. This liquid, or the particles consisting this liquid, are at rest. So therefore, there can be no static friction in fluid mechanics. So friction cannot develop when the liquid is at rest. So that's why if you have a glass of water, you look at the surface of the water, it should be flat. It should be horizontal for the mass of water to be at rest, or mass of liquid to be at rest. So therefore, let's rotate the plane. So for this surface to be, or for this mass of water to be at rest, then the surface should be horizontal like this. And if this is the section parallel to the surface, then that's the time that the pressure is, or the liquid, the mass of liquid is at rest, and so the pressure, which is represented by the reaction at this contact surface, which is equal to this normal force, should be coincident and equal with the weight, which is vertical. So that's the weight, and this is the uh, reaction in a form of pressure at the surface here, and this total pressure should be equal to this normal force, and this normal force must be equal to the weight for this liquid to be at rest. So that's why we only see liquids that have horizontal surface to be at rest. Then the next is at any point in a fluid at rest, the pressure is the same in all directions. So let's prove this statement. So let's consider a point. So remember, this is a point. So supposedly this is dimensionless, but let me show to you that the pressure is the same in all directions. So these are the dimensions: differential x, differential z, and differential y. So remember, this is a point. That's why the dimensions should be very, very, very small. So in fact, there should be no dimension because it is a point. But for the purpose of clarifying the concept that the pressure is the same in all direction at a point in a fluid at rest, so let's have this uh, point, and the point has this triangular wedge-like shape. So the angle of inclination of this face is theta, same history with that, and the area of this inclined face is the differential A, and the pressure perpendicular to this, it should be perpendicular to the surface from the result of Pascal's law here, the first statement, then it should be perpendicular normal. So therefore the force, differential force acting normal to this inclined surface and through the centroid of supposedly this very, very small area dA is differential Fn. And this differential Fn is equal to the pressure, which is the same because this is a point. So the pressure has the same intensity of Pn perpendicular to the surface times the differential area. So along x towards the positive x-axis, let's call the pressure there as P sub x, which is also uniform because this is a point and the area is very, very small. So the total pressure is equal to P sub x times the area of that uh, end, which is equal to dy times dz. So summation forces x equals 0. And take note that the angle that dFn makes with the vertical is also theta from the result here. Then this is dfx. So dfx minus p sub n sine of theta equals 0. So in other words, differential fx, which is equal to pressure x times the projected area over which the pressure acts, is differential z times differential y, or dy dz. That must be equal to p sub n times dA, where dA is equal to the length of this inclined surface of a point. So remember, this is a point, and it is square root of dx squared plus dy squared, then times dz. That's the area. Then the x component is multiplied by sine of theta. So take note that this hypotenuse is square root of dx squared plus dy squared. If we multiply that by sine theta, then it is equal to dy. So this square root of dx squared plus dy squared is actually equal to dy times sine theta. So that is equal to dy. So replacing this expression by dy, then after that we cancel out these common factors dy and dz. So that proves that px equals pn. Similarly, summation forces y equals 0. So the pressure acting on this horizontal uh, surface of this point is p sub y, and therefore the force is upward, equal to py times the area, which is equal to dx times dz, because that's a point. So these are the dimensions, equals the vertical component of dfn is dfn times cosine theta, and dfn is pressure n times area, and the area is dz times this inclined uh, length, which is square root of dx squared plus dy squared, then times cosine of theta. And again, square root of, or hypotenuse times cosine of theta is equal to dx. So this represents dx, replacing this quantity by dx and canceling out similar factors, dx and dz. So we conclude that py equals pn. Of course, summation forces along Z is proven to be in equilibrium because we have the same area. So the pressure is PZ, and we will just call the pressure in this direction towards the positive Z direction as PZ, and the pressure on this face in the opposite direction as PZ prime, and they have the same area, so therefore they are equal. So PZ equals PZ prime, and I'm not showing the pressure anymore because the figure becomes very complicated. So let's just imagine that the pressure towards the Z direction is PZ, and the pressure in the opposite direction is PZ prime, and they have the same area of this triangle. So therefore, we can cancel the area and have this result PZ equals PZ prime. In short, we have proven that one statement by Pascal, which states that at any point in a fluid at rest, the pressure is the same in all directions, is true. So that is, we have Px equals Py equals Pz equals Pz prime equals Pn, and so on and so forth. So if we have here a liquid surface which is at rest and we have a point here, the pressure may be directed rightward, upward, leftward, downward, with the same intensity of pressure, up to the right, down to the up to the left, then down to the right or down to the left, or any direction, and the intensity is the same because we are talking about pressure at a point, and the point is dimensionless. Later, we show that the pressure is really the same or constant at a point in a homogeneous fluid at rest, at all points in a homogeneous fluid at rest. So this is the proof, and we have shown that the pressure may be directed anywhere. So later on, when we have a surface, then the pressure should be perpendicular to that surface. The intensity of pressure at a point is the same in all directions. That's the second statement by Pascal. So next, we define pressure as the result when a force is distributed over an area. So for example, we have a footing or a dam here, and because of the weight of the dam or the forces, loads transmitted to this structure, this may be a footing, then we expect a pressure distribution, which is in general assumed to be here because that is not known. And engineers make this pressure diagram straight line, or the intensity of pressure varies, but let's just make it this way because the actual pressure diagram is not really known, but I'm sure it varies. So we notice that the pressure intensity is not uniform, but if we consider a very small area, then that intensity of pressure will be uniform or constant over that very small area. So the idea therefore is that the total pressure or the volume of this pressure diagram should equal to the weight, and the weight and this volume of this pressure diagram here must be collinear in action so that they are in equilibrium, or the system will be in equilibrium. So again, for the pressure to be uniform, we should consider a very small area. So let's call the intensity of pressure at the left edge here as PL and at the right as PR. And for that pressure to be uniform, as I said, we should consider a strip and or a stick, so that the volume of this stick is constant, equal to the area, which is very small, differential area. So that's the differential area rotated, then times the intensity of pressure, which is denoted by P for that case. So the force, therefore, is also differential force because we are considering only a very small area. So the product of area and P, differential area times P, is supposedly volume, but we expect that pressure should be in kilonewton per square meter or per square unit, and the area is in square unit. So therefore, the product of differential area and P, differential area times height, which is geometrically interpreted as volume, will give us a unit of force. So that's why the volume of this differential volume of this pressure diagram over this very small area is differential force. So differential F is differential volume of pressure diagram, and this is equal to P times dA. Therefore, the expression for pressure is it is equal to differential force over differential area. So this is the expression or formula for the constant pressure. So it suggests that the area must be very, very small for the intensity of pressure to be constant so that we can compute it. So thus pressure or the intensity of pressure is uniform only when considering a very small area dA. So let's now have variation of pressure with depth. Having established this formula for pressure or differential force is equal to pressure times dA. So let's consider a body of liquid. So let us say this is the body of liquid, and this liquid here is at rest, of course. And let's consider a prism of this liquid. So to see the prism, do not imagine. So let's put the boundary of that prism. So this is the same substance as this liquid here. It may be water, and this is the prism of water so that we can isolate it. So the end area is very small. The length is denoted by L, and the angle of inclination that the axis makes with the horizontal is denoted by theta. So I'll call that higher point as 1, the lower point as 2, the length as L. And so the end area is differential area, very small. Therefore, because the area is very small, the intensity of pressure here is uniform. So the pressure over section 1 is P1, and it is uniform. If you multiply that by differential area, so that's the force that pushes or compresses point 1. By the way, when you say pressure, it is understood compression. So in fluid mechanics, pressure is positive when it is in compression. So it is very opposite to the mechanics of materials or in strength of materials where tension is positive. But here we are talking about pressure, so it is understood positive when in compression. So that's dA. So the force is directed toward point 1, and there is also a force directed towards section 2, which is compressing point 2, and the area is the same dA. So therefore, since this angle is denoted by theta, the vertical distance, if the length or the length of the prism is L, then the vertical distance between them is denoted by h, which is L sine theta. So considering the free body diagram of this prism, we have the weight, and we have forces at 1 and 2. So the force at section 1, which compresses point 1, is dF1, and dF1 is equal to P1 times dA. Take note of that from the result here. Differential force is pressure times dA because dA is very small, so the intensity of pressure is uniform. At section 2 also, which is up to the right, it is equal to dF2. And it is equal to pressure at 2 times differential area. Now, because this prism is in equilibrium, we will only analyze the axis or the forces or components of forces along this axis of the prism, and we'll call that x-axis. So this is the y-axis, which is perpendicular to the x-axis, so that the weight has component along the x-axis but in the opposite or negative direction. So remember, that's also theta, and the length is L, so that this vertical distance h is L times sine theta. And this is the component of the weight, which is W times sine of theta. So summation forces X equals 0 because the prism of liquid is in equilibrium. So we have dF2 minus W sine theta minus dF1 equals 0, or dF2 equals dF1 plus W sine theta. So replacing dF2 by P sub 2 times differential area, dF1 by P1 times differential area, and weight is gamma times differential volume. Remember that from physics. So specific weight of liquid times the volume, which is we call differential volume because the prism is very small. And the angle, the component is gamma times dV times the sine of theta. So replacing differential volume by area times length, differential area times length rather. So we can cancel dA, which is common to all terms, left and right side of the equation. So canceling out dA, we have P sub 2 equals P sub 1 plus gamma times L sine theta. And take note that L sine theta is h, the vertical distance between points 1 and 2. Therefore, the pressure at point 2 is simply equal to P1, the pressure at the higher point, times gamma times h. So it means that the pressure at the deeper point is greater than the pressure at a higher point in a fluid at rest, or in a liquid, homogeneous liquid at rest. So that means P2 minus P1, the difference in pressure between 1 and 2, is simply the product of the specific weight of this liquid, or the weight density of the liquid or fluid in general, times the vertical distance between points 1 and 2. So the idea is the pressure at the deeper point is higher than that at higher point. And I hope that you can remember that, because you can charge that to your experience when you swim into the ocean. So the pressure really increases if you swim into deeper points. If you submerge your head into deeper point, you will feel that the pressure increases. But if you just submerge your head at a shallow depth, then you can feel the pressure, but that's not that high or great as compared to when your head is submerged into a deeper point. So when h is 0, or that is when points 1 and 2 are on the same plane, then h is 0. So if h is 0, from this formula here, we conclude that the pressure is the same. So remember, therefore, at all points in a homogeneous fluid at rest, at all points on a horizontal plane, in a homogeneous fluid at rest, the pressure is the same or equal. So that is, if we have points A, B, C, and D, then because they lie on the same horizontal plane and they are exposed to the same fluid or liquid, then the pressure is the same. So P sub A equals P sub B equals P sub C plus equals dot 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 P sub Z, or any point on the same horizontal plane, the pressure is the same. So that's a very important principle also that you must know. Then what if point 1 is, or therefore if we have a point here, then the intensity of pressure is P, which is equal to, it is equal to P, then you can direct it in any direction. That's Pascal's law, which we verified in the preceding slides. So that's it. So when point 1 and point 2 lie on the same horizontal plane, h is 0, so therefore P1 equals P2 as a result. So I have this figure again so that we can see here that the pressure is the same at all points lying on the same horizontal plane, as long as the fluid is homogeneous. So at all points on a horizontal plane in a homogeneous fluid at rest, the pressure is the same. That's the statement by Pascal's, and we have shown here that it is true. So when point 1 is on the liquid surface, P sub 1, the gauge pressure there is 0 because it is exposed to the atmosphere. So the gauge pressure is 0. By the way, gauge pressure is, we call that pressure, gauge pressure is 0, and point 1, which is exposed to the atmosphere, when we compute the absolute pressure, then it is atmospheric. So if there's no given information about the atmospheric pressure, then we always assume it is a standard atmospheric pressure, which is equal to 101.325 kilopascals absolute, which we can make 101.3 kilopascals absolute so that we can easily remember it. So P is equal to gamma times H. So if P1 is 0, so P sub 2 is gamma times H as a result, or in general, the pressure is equal to gamma times H, where H is called the pressure head. So that's the pressure at any point below a liquid surface, where that surface of the liquid is exposed to the atmosphere, or the pressure there is 0. So H is P over gamma. This is called pressure head. This pressure head is thought of as the depth of liquid, so that at the bottom of that depth, the pressure P is developed. So that's the idea of what pressure head is. So it is the depth of liquid producing a pressure P at the end of this depth. So since friction cannot develop when the fluid is at rest, the pressure is always acting normal to the surface it contacts. So this is already proven in the preceding slides. So we have this Pascal's law that at any point in a fluid at rest, the pressure is the same in all directions. We have already presented that. So that let's have a demonstration here. So if I call this point 1 at this corner here, then because there are two surfaces, one is horizontal, the other is vertical, you can make the pressure P1 to be directed to the left or directed downward, as long as it is compression or pressure. So because this corner here is at the same level as 1, by principle stated earlier, the pressure at all points on the same horizontal plane in a homogeneous fluid at rest is the same. So the intensity of pressure here is also 1. Now we have here an inclined surface, therefore the pressure here may be directed downward, perpendicular to this horizontal bottom, or directed down to the right, perpendicular to this inclined surface. At point 2, then we have also two pressures. One is perpendicular to the surface, and the other one is horizontal to the right, depending on which direction you want to uh, compute or reveal in your figure, in the figure. So again, at point 1, we have downward because we have a horizontal surface, and leftward because we have this vertical surface. At this point, this is also marked point 1 because the pressure is the same. So we have downward because it is perpendicular to the surface, and down to the right, perpendicular to this inclined surface. But the intensity of pressure is the same. At point 2, the intensity is lower, smaller, because point 2 is higher than point 1. One is rightward and the other is perpendicular to the surface. So let's test your uh, understanding of the principles I presented here. So let's have here a tank, and we have here open piezometers connected. So we have different fluids here. This is gas, and this is, so remember, a gas is very, very light. So if you are in a confined room, then if you are lying and you are standing, you will feel the same pressure. You will not feel headache when you lie down, or you will stand. It's the same feeling. So therefore, whenever you are or whenever you encounter a gas compartment, then the pressure is just the same anywhere in the space, unless otherwise the specific weight or weight density of the gas is given, and you are required to compute the difference in pressure, but the difference in pressure is very, very small. So in short, when you are uh, confronted with a gas compartment, the pressure anywhere, you choose any point in the gas compartment, the pressure is the same or uniform. So I'll call that point 1. Then is we have here an open piezometer. This is open to the atmosphere. Is the If the pressure is the same, then you mark that with the same number. You just put prime. So is this 1 prime? Is the pressure here 1 prime? The answer is yes, because the intervening passage between this point and that point is filled with the same liquid. So in other words, you go down, then you go up, we have the same liquid. So therefore, we call that 1 prime. The pressure is the same. So 1 prime. Now, how about this point? This is a different point. They have different elevations. So therefore, this is another point called that point 2. How about this point here? Is the pressure here the same as that of 2? The answer is yes, because between 2 and this point, you cannot, the only way we can proceed to this point is to pass through this tube here. And since this tube is filled with the same liquid, then the pressure here is equal to pressure at 2. So we mark this as 2 prime. Remember the principle that when at all points on a horizontal plane in a fluid at rest, homogeneous fluid at rest, the pressure is the same. So that's why it is 2 prime. Now, how about this point here? This point is exposed to the atmosphere, so the pressure here is different from that of 2 and from that of 1. So that's why we call that point 3. So if we have a horizontal line through point 3 and this point here, which is same level as 3, then the pressure will be different, because the passage or to reach point 3 is we must go here, and we have liquid 1, then another liquid, so the liquid is not homogeneous. So therefore, even if they are on the same horizontal plane, the pressure will be different. Now, how about this point? This point is also exposed to the atmosphere, and this is air, and air is a gas. Therefore, because air is considered weightless, therefore, we expect these points have the same exposure. So just like a person in the ground floor and a person in the second floor, then they have the same feeling. If you transfer to the second floor, you will feel the same, because you are surrounded with air, and the pressure is considered the same, or gas, it's the same. So therefore, the pressure here is denoted by, or the point here is denoted by 3 prime. The pressure are the same even if they do not lie on the same horizontal plane, but because this point 3 and this 3 prime are exposed with the same gas, which is air. So that's why that's denoted 3 prime, and the pressure is 0 actually, because 0 gauge, because it is exposed to the atmosphere. So therefore, if we have a point here which is the same level as this point, then this should be marked different point, point 4, even if they lie on the same horizontal plane, because to reach point 4 from point 2, we must go through this opening here, intervening passage, and we pass through 2 different liquids, and therefore the liquid is not homogeneous, so the pressure at point 2 is different from the pressure at this point here, although they lie on the same horizontal plane. The fact that, as I said, the fluid is not homogeneous. So it is marked as 4. This one, because this is also exposed to the atmosphere, it has the same pressure, which is 0, as that of 3 prime and 3. So therefore, that is 3 double prime. Then this point, of course, is different from 2 and any other points there. So we'll call that point 5. And if we draw a horizontal line, so these 2 points are on the same level. And to reach this point here, we must pass to this uh, passage. And since we have to pass same liquid, they lie on the same horizontal plane. Therefore, this is also marked 5 prime. The pressure at 5 is equal to that of 5 prime. So that's it. And I hope that you know the principle already. So this is a different point, call that point 6. If we draw a line, horizontal line through this point, this is 6 prime. They have the same pressure. Why? Because to reach 6 prime, we have to pass here, and we only pass one same liquid homogeneous, so the pressure is the same. However, this point is different because we have this liquid here, and we have another liquid. So this is 0.7. So that's the principle to this uh, principle about pressure. So I hope that you retain the principle and you can recall it when you solve problems about calculations of pressure. So let's have the first example. So water stands in an open tank that is 2.7 meters high at a depth of 2.4 meters. So determine the pressure at the depth of 1.8 meters and express this pressure in kilopascals, kilogram per square meter, pounds per square inch, this is PSI, and bars. And number 1.5, also determine the maximum absolute pressure in kilopascals. So let's draw a tank. So let's sum up pressure from point 1 to point A. So SUP means sum up pressure. So this is the figure we have. Let's call this point 1. This is point A, which is 1.8 meters from point 1. And of course, the depth of liquid in the tank is 2.4 and the height of the tank is 2.7. So let's sum up pressure from point 1 to point A to compute the pressure at A. So first, we have P1 going down. Remember that pressure increases with depth because the pressure at the deeper point is higher compared that at the upper point. So the increase in pressure is simply gamma of the liquid times the vertical distance between the 2 points. So in this case, the specific weight or gamma of water is 9.81 kilonewtons per cubic meter unless otherwise given in the problem. So we should use 9.81 kilonewtons per cubic meter. And the height is 1.8, so 9.81 times 1.8. Then we now reach point A, so we equate this pressure to pressure at A. We take note that point 1 is exposed to the atmosphere, so therefore the pressure there is 0 gauge. So 0 plus 9.1 times 1.8 equals P sub A. So solving for P sub A, 17.66 kilopascals. By the way, if there's no description as to the type of pressure that is to be solved, then it is understood gauge pressure. Because if it is absolute pressure, it is specified in the problem or it is clear, especially in the phenomena of gases. So pressure that is measured is meant to be gauge pressure. So this is gauge pressure. If there's no extension letter A, so that's gauge pressure. So 1.2, let's convert this to kilogram per square meter. First, we multiply 1,000 Newton per kilonewton to convert that to Newton per square meter or pascals. So we can cancel kilonewtons. Then we multiply 1 kilogram, which corresponds to 9.81 newtons. So 1 kilogram is 9.81 newtons. So finally, we can cancel newtons also. The unit now is in kilogram per square meter. So pressure at A in kilogram per square meter is 1,800 kilogram per square meter. So by the way, we have to round off values to 4 significant figures, and that's 4 significant figures. Next, let's convert it to PSI. So we begin with 1,800 kilogram per square meter. So we multiply this by 2.205 pounds is 1 kilogram. Then after that, we note that 1 meter is 3.281 feet. Then we have to square it. 1 meter is 3.281 feet. So quantity square. Then the unit now is cancel kilogram. So pound per foot square. And finally, we multiply 1 foot per 12-inch quantity square. So that would now be in pounds per square foot. So using your calculator, pressure at A is 2.560 psi. So that's it. And next is the maximum pressure in bars. By the way, 1 bar is 100 kilopascals. So that's the conversion. That's the equivalent of 1 bar. So PA 17.66 kilopascals. We multiply that by 100. We multiply this by 1 bar per 100 kilopascals. So beginning with 17.66 kilopascals, so it is 0.1766 bar. So that's the pressure in bar. Then the maximum pressure occurs at B. So we sum up pressure from 1 to B, and take note that the pressure at 1 is 0. So pressure B is Pmax equals P1. Then we go down plus gamma of water times 2.4. So solving for maximum pressure, it is 23.54 kilopascals. So that's the maximum pressure. Okay, for the next example, we have this problem. What would be the temperature and pressure of nitrogen gas at 30 degrees Celsius and 120 kilopascals absolute if it were compressed isentropically to 50% of its original volume? So take note that the process, thermodynamic process involved is isentropic process. And also take note that nitrogen gas is a diatomic gas. It is denoted by N2. There are 2 atoms, and for diatomic gases, the isentropic exponent K is 1.4. So the relationship between final temperature, absolute temperature ratio to volume ratio is T2 over T1 is equal to V1, volume 1 over volume 2 raised to isentropic exponent K minus 1. Then it is also equal to pressure, final pressure 2 over P1 initial raised to K minus 1, quantity K minus 1 all over K. So again, the equation is T2 over T1 equals quantity V1 over V2 raised to K minus 1. And it is also equal to quantity P2 over P1 raised to quantity K minus 1 over K. So that's the relationship. You just look at the derivation in in the previous or in my handouts. So first, let's have this equation here. Remember that T2 over T1, these are absolute temperature. So in Kelvin, so T2 should be in kelvins, T1 should be converted to Kelvin. So we add 273 to 30 Celsius. So T2 over 30 plus 273 equals V1 over 0.5 of V1 raised to 1.4 minus 1 because the final volume is 50% of the original volume. And it is equal to P2 over 120. P1 initial is 120 raised to 1.4 minus 1 over 1.4. So T2 over 303 equals, this is 2, cancelling out V1, 2 to the 0.4 equals P2 over 120 raised to 2 over 7. If we simplify this, 2 over 7. So for this relation, T2 over 303 equals 2 to the 0.4. So T2 is equal to 399.8 kelvins. Then T2 in degrees Celsius, we subtract 273. So temperature in degrees Celsius plus 273. So T2 is 399.8 minus 273. So it is 126.8 degrees Celsius. Likewise, for this equation here, 2 to the zero point 0.4 equals P2 or 120 raised to 2 over 7. We raise everything to reciprocal of 2 over 7, 7 halves. So 2 to the zero point 0.4 raised to 7 halves equals P2 over 120. So finally, P2 is equal to 120 times 2 to the 1.4. So 0.4 times 7 over 2 is 1.4. So P sub 2 in kilopascals absolute is 316.7 kilopascals absolute. So that's it. For the next example, a closed vertical pipe contains layers of fluids, namely gas of thickness 1 meter under pressure of 60 kilopascals, ethyl alcohol of thickness 60 meters and density 780 kilogram per cubic meter, oil of thickness 10 meters and density 840 kilograms per cubic meter, water of thickness 2 meters and density 990 kilograms per cubic meter, glycerin of thickness 3 meters and density 1236 kilogram per cubic meter, and the remaining is molasses of thickness 10 meters and density 1,500 kilograms per cubic meter. Assume the fluids are separated and do not mix. So, in which fluid is a pressure of 610 kilopascals first achieved? If the bottom of the pipe is at elevation 0, what is the pressure at the bottom in kilopascals? Then, next question, at what elevation is a pressure of 640 kilopascals occurring? Then, last question, if an open piezometer is attached at the side of the pipe anywhere on the oil portion, determine the elevation of the liquid level in the piezometer or in the tube. So this is the pipe. This is gas, 1 meter thick, but the thickness is not important because this is inside here is a gas and the pressure is constant at 60 kilopascals there. So then followed by that's 60 kilopascals, 1 meter, then 60 meters, we have ethyl alcohol, then oil of density 840, thickness 10 meters, then water 2 meters, glycerin 3 meters, then the rest is molasses 10 meters thick. So water, glycerin, then molasses. So for the first question, in which fluid is a pressure of 610 kilopascals first achieved? So we mark these interfaces with 1. The pressure at 1 is 60 kilopascals, of course. Call that point 2. Point 3, interface between oil and water. Point 4, between water and glycerin. Point 5, between glycerin and molasses. Then B at the bottom of the tank, or B is as in bottom. So to solve for pressure at point 2, we sum up pressure between 1 and 2. So P1 plus specific weight of ethyl alcohol is density times G, 9.81 newtons. So that would be kilogram per cubic meter. Density times 9.81 is newtons per cubic meter, the specific weight of ethyl alcohol. Then, so 780 times 9.81, that would be newtons per cubic meter. We want the answer to be kilopascal, so we divide 1,000 newtons per kilonewtons. So the unit now here is in kilopascals. So for the next calculation, we simply divide the density by 1,000, and the result after multiplying 9.81 and the depth, the result would be kilopascals. So gamma times depth. So going down is positive because the pressure increases with depth. So equals pressure at point 2. So substitute P1 equals 60. Then the value here is 459.108 equals P2. So rounding off to 4 significant figures, the pressure at 2 is 519.1 kilopascals. We want the pressure 610 kilopascals. So it is not yet occurring at point 2. So next, we sum up pressure between 2 and 3 to find the pressure at 3. So pressure at 2 is 519.1 plus gamma of oil is again 840 divided by 1000, so 0.84 times 9.21 times 10. So this is now in kilopascals. Then we get pressure at 3. Pressure at 3 is 601.5 kilopascals. So 601.5 kilopascals is still less than 610. So let's proceed to computing pressure at 4. So sum up pressure between 3 and 4. So 601.5 plus 0.99. So 0.99, 990 divided by 1000 times 9.81 times 2 equals pressure at 4. So pressure at 4 is 620.9 kilopascals, which is now greater than 610 kilopascals. Since at 3 the pressure is less than 610 kilopascals, it's only 601.5. At 4 it's 620.9, which is greater than 610 kilopascals. So we are sure that the pressure of 610 kilopascals is first achieved in somewhere in the water portion. So our answer, pressure of 610 kilopascals is first achieved in water. So that's the answer to the first question. Number 2, if the bottom of the pipe is at elevation 0, what is the pressure at the bottom in kilopascals? Since we already know the pressure at 4, so we sum up pressure from 4 to bottom to B. So pressure at 4 is 620.9 plus glycerin 1.236 times 9.81 times 3. Originally 1236 divided by 1000. So to make the unit consistent in kilopascals, then plus 1.5 times 9.81, 1500 over 1000, so 1.5 times 9.81 times 10 equals pressure at the bottom B. So computing for pressure at the bottom B, it is equal to 804.4 kilopascals. Then question number 3, at what elevation is a pressure of 640 kilopascals occurring? So 640, the pressure at 4 is 620.9. So let's compute the pressure at 5. We are sure that it is somewhere in the glycerin portion. So, but anyway, let's compute the pressure at 5 by summing up pressure from 4 to 5. So pressure at 4 is 620.9 plus 1.236 times 9.81 times 3 equals pressure at 5. So pressure at 5 is 657.3 kilopascals, which is greater than 640 kilopascals. So it is somewhere on the glycerin portion. So we will call that point there where the pressure is 640 kilopascals as point A, and its thickness or distance from the interface between glycerin and molasses is, let's call that Y1. And so the elevation of point A where the pressure is 640 kilopascals is 10 plus Y1. So Y1 is important since we are accustomed to summing up pressure from higher to lower. So let's do that here. So sum up pressure from point A, which wherein the pressure is 640 kilopascals, to point B. So sum up pressure from A to B, and the pressure at the bottom is 804.4. So pressure at A is plus 1.236 times 9.81 times Y1 plus 1.5 times 9.81 times 10 equals pressure at B. Substitute pressure at B and pressure at A, which is 640. Then solving for Y1, so Y1 is 804.4 minus 1.5, 9.81 times 10 minus 640. Then all over this quantity 1.236 times 9.81. So Y1 is 1.423 meters. Then adding 10, that's the elevation at point A where the pressure is 640 kilopascals. So elevation at A is 11.423 meters. So let's just, you may have your final answer 11.42 if we round that off to 4 significant figures. Then the last question is, if an open piezometer is attached anywhere on this ethyl alcohol oil portion rather, so what would be the elevation of the oil surface in the tube. Of course, it's oil that will enter this tube here. So we will call that point 6. No? So we have here point 2. Then this is at the same level as 2, and we have the homogeneous fluid, which is oil. To reach this point, we have to go here. So it's the same fluid, therefore the pressure here at the same level as 2 is 2 prime. They have the same pressure. Then we will call the distance from 2 prime to that point as y2. Of course, the figure should be beyond, it extends above because the pressure here is very high. But because of limited space, let's just call that y2. And let's call this point 6. Then we sum up pressure from 6 to 2, or 2 prime. And take note that the pressure at 6 is 0. So sum up pressure from 2 prime. So let's have 2 prime to 6 this time, so that we have a direction which is upward. So we have to subtract the gamma of oil times times y2 from the pressure at 2 prime. So we have pressure at 2 prime minus, it's minus because it's going up, 0.84 or 840 over 1000 times 9.81 times y2, the height or the thickness, equals pressure at 6. And pressure at 6 is 0, and P2 prime is equal to P2, which is equal to 519.1 minus 0.84 times 9.81 times y2 equals 0. So solving for y sub 2 is 62.99 meters. So therefore, the elevation of the liquid oil surface in the tube is 10 plus 3 plus 2 plus 10 plus y2. So elevation at point 6 is 10 plus 3 plus 2 plus 10 plus 62.99. So it is 87.99 meters. As I said, it should be above the top. So that's it for this problem. So for example 4, in the figure shown, fluids A and B have specific gravities of 0.915 and 2.95 respectively. Compute the pressure at point M in meters of fluid A. So it's pressure head at M in terms of fluid A. If the pressure at M is increased by 6.9 kilopascals, how many mm will fluid B rise in the 12.5 mm diameter tube? So this is the figure. So let's mark this point as 1. The pressure at 1 is 0. It is exposed to the atmosphere. So this point as 2. Then same level. So this is 2 prime. Same pressure because from 2 to 2 prime we pass same liquid, homogeneous liquid. And from 2 to this point here, same pressure because from 2 to this point here, they lie on the same plane, and to reach this point, we pass the same homogeneous fluid, which is fluid A. So that's 2 prime. Then this is now point M. So sum up pressure from 1 to M. So beginning at 1, the pressure is 0, then plus 2.95 times 0.372. 2.95 times gamma of water, 9.81. Specific gravity times specific weight of water gives us the specific weight of this fluid B here. 2.95 times 9.81, that's the specific weight of fluid B, times the vertical distance, which is 0.372. It is plus because we go down from 0.1 to 0.2. Positive if we go down. The pressure increases as we go down. Then from 2, we jump across to 2 prime, and from 2 prime, we jump across to 2 double prime. Nothing changes in the pressure because all these 3 points lie on the same horizontal plane. And take note that from 2 to 2 prime, we pass the same liquid, and from 2 prime to 2 double prime, we also pass a homogeneous liquid, so the pressure does not change. Then 2 prime to M, so that's going down, so plus gamma of fluid A is 0.915 times 9.81, that's the gamma of fluid A, times 0.415, then equals pressure at M. So solving or calculating these values, so P sub M is equal to 14.49 kilopascals. But the question is pressure at M in meters of fluid A. So that's the pressure head at M in terms of fluid A. So it is PM over gamma of fluid A. And the gamma of fluid A is 0.915 times 9.81. So 14.49 over 0.915 times 9.81. So the equivalent pressure head at A at M in meters of fluid A is 1.614 meters of fluid A. Then for the second question, if the pressure at M is increased by 6.9 kilopascals, then imagine that this is a bulb, then you press this or you compress this. So the pressure will be transmitted, this will be pushed down, and therefore point 1 will rise. So the result would be this. So this is now the figure, and that would happen. So there is a displaced fluid A here, and since the same tube, only this part will be displaced also. So the analysis is the decrease in volume here is equal to the increase in volume at the top. So that we will call this drop in thickness in this bigger reservoir, 125 mm diameter, as delta Y, and the increase in height there as H. So we will mark this point exposed to the atmosphere as A, then this point as B, same pressure as this, so B prime, same pressure as this as B double prime, same explanation as before, then Mn. So we sum up pressure from A to Mn. Take note that the pressure at Mn is equal to 14.49 plus the increase in pressure of 6.9. So sum up pressure from A to Mn. So we have pressure at A, which is 0, plus 2.95 times quantity H plus 0.372 plus delta Y. So we reach point B. Jump across, then go down. So plus 0.915 times 9.81 times this vertical distance is 0.415 minus delta Y. So 0.915 times 9.81 times 0.415 minus delta Y equals pressure at N, which is 14.49 plus 6.9. So distributing this factor here with H, so and simplifying, so we have 28.9395 H plus 10.7655 plus 28.9395 delta Y. Then this value here times 0.415 is 33.7251 minus 8.9762 delta Y. Then this combined value is equal to 21.39. So combining like terms, we have delta Y like terms here. So 9395H plus 19.9633 delta Y. Then 21.39 minus 3.7251 minus 10.7655 is 6.8994. Call this equation 1, which is very important. Next is the volume displaced here in this reservoir here is equal to the volume increase here. So the volume V1 represented by this displaced volume here is equal to area of this reservoir times delta Y. And the volume in the cylindrical part, these are two cylinders, this is 12.5 mm in diameter, is equal to area times H. So that is V1 equals V2. So pi over 4 times 125 square times delta Y equals pi over 4 times 12.5 square times H. So cancel pi over 4 and express delta Y in terms of H. So delta Y is 0.01 of H. Substitute this into equation 1, then we can now solve for H. So 28.9395 H plus 19.9633 times 0.01 H equals 6.8994. Solving for H, first its unit is in meters. So 0.2368 meters, then times 1,000, it is 236.8 mm. So that's it for this problem. So for the next problem, this is on Boyle's law. A uniform tube closed at one end and open on the other end is immersed vertically in water with the open end down. If the water rises in the tube 2 meters, determine the distance of the open end of the tube from the water surface if the tube is 3 meters long. Neglect vapor pressure and assume standard atmospheric pressure. So even if without this statement, so we really have to neglect vapor pressure so that we can analyze this problem and assume atmospheric pressure unless otherwise specified in the problem. So this is the tube. So as stated, the water rises 2 meters. So this is 2 meters. Therefore, the depth or the height of the trapped air would only be 1 because the total height of the tube is 3 meters. So this is 2 meters. That's 1 meter. And we will call the distance of the open end to the water surface as capital H, and we call the distance of this point interface between gas trapped air and this point as point 2, and the distance is small h. So remember that the pressure at point 2 inside the tube and this point outside, because they lie on the same horizontal plane and we have a homogeneous fluid to proceed from 2 to 2 prime, we have the same homogeneous fluid and they are on the same horizontal plane, so the pressure is the same. So if we call this a small h, P1 is the absolute pressure at point 1 which is exposed to the atmosphere, so that's atmospheric, which is 101.3 kilopascals absolute. The pressure at point 2 is P1, which is 101.3 kilopascals absolute, plus gamma of water times the vertical distance is h. And of course, V1 is the volume of the tube, original tube, because this is empty and it is filled with air outside when it is at the above the water surface, and it is equal to area, which is constant, times 3 meters, while V2 is the volume of the trapped air final is area times 1. So P1 V1 equals P2 V2, where P1 is atmospheric and it is 101.3 kilopascals uh, absolute, so it is standard. And V1 is the volume of initial volume of the air, which is the volume of the tube, area times 3. P2 is area P1 101.3 plus 9.81 times H. Then V2 is the volume of this top air, which is area times 1 meter. Cancel out A, so 101.3 times 3 equals quantity 101.3 plus 9.21 times H. So 101.3 times 2, because we have to subtract 101.3 divided by 9.81 is equal to 20.65 meters. Therefore, from the figure, capital H is small h plus 2. So 20.65 plus 2 is 22.65 meters. So that's it for this problem. So for the next problem, example 6, if exactly 20 bolts of 2.5 cm diameter are needed to hold the air chamber together at section AA as a result of high pressure within, how many bolts will be needed at B? So this is the figure, and because this is filled with air chamber, the pressure at A by principle is equal to the pressure at B. So what is pressure? Force, total force in the bolts in section A divided by area of section A, that's the pressure at section A, equals total force due to the force in the bolts at B divided by area at B. So PA equals P sub B, that's the principle. And PA is FA divided by area A equals PB is force, total force in the bolts at B divided by area B. So the force at A, so of course, because these are identical bolts, the bolts should be equally stressed, or each bolt has the same force. So therefore, the total force at A is equal to number of bolts at A times the force in 1 bolt. And force at B is number of bolts at B times the force of 1 bolt at B. And area A is pi over 4 50 square. Area B is pi over 4 25 square. So again, N times F, NA times F of 1 volt over pi over 4 50 square equals NB times F of volt divided by pi over 4 times 25 square. So we can cancel pi over 4 and force in the bolt, so that it reduces to NA over 50 square equals NB over 25 square, where NA is 20. So substitute NA 20, you'll get NB equals 5 volts. 20 times 25 square over 50 square. So NB is 5 volts. So that's it for this problem. So this is our last example. What is the bulk modulus of elasticity of a liquid that has a density increase of 0.025% for a pressure increase of 1.2 megapascals? So take note that the original formula for bulk modulus of elasticity is equal to negative differential pressure over differential volume over volume. So relative ratio of volumetric change. So if you have a given mass of liquid, when you compress it subjected to this pressure, take note that the mass is constant. It's only the volume and the density that change, and therefore, since only the density and volume change, it's the density and the volume that change, and the mass remains unchanged, so mass is constant. So we begin by the formula mass equals density times volume. So if we obtain the differential of this formula, the differential of mass, which is constant, is 0, and we have differential of product, which is which is density times differential of volume plus volume differential of density. So we set differential mass equals 0 because it is constant, and setting up the ratio negative differential volume over volume, it is equal to differential density over density. The original formula for bulk modulus of elasticity is negative differential pressure over differential volume over volume. So we replace this negative of differential volume over volume by differential density over density. So bulk modulus of elasticity therefore is equal to differential pressure over differential density over density. So it is positive. So the original formula, there is a negative sign preceded because the change in volume is negative. So that negative is positive. Why? Because when you compress a certain volume, the final volume expected is lesser than the original volume, which is V. So therefore, final volume minus original volume would be negative, represented by that dv there. So that's why a negative sign is preceded. Whereas the change in density is positive, or it is increasing, because take note the mass remains constant and the final volume is lower slightly than the original volume. So therefore, mass constant over volume, which is lesser than the original, will increase. So that's why the sign here is positive. So substituting values, bulk modulus of elasticity is 1.2 megapascals divided by 0.025 over 100, because that's 0.025%. So ISA B is 4,800 megapascals divided by 1,000. So ISA B, bulk modulus of elasticity of the liquid, is 4.8 gigapascals. So that's it for this video. I hope that you learned something from these examples and from the discussions, and I hope that you can solve problems related to these examples here. So what is important would be the principles, and I hope that I explained it satisfactorily to my audience, and I hope that you enjoyed watching. Bye bye.